concentration at the following point. So we have 15 meters above ground level, so that tells me Z is 15 meters. We're 800 meters downwind from the stack, so that tells me our X is 800 meters, or 0.8 kilometers as we usually use it. And then we're 200 meters off the center line, which means our Y is 200 meters. And we're looking for the concentration steady state in micrograms per cubic meter. So for this, we will do the following. We have an equation. C is equal to Q divided by 2 pi U, our dispersion constant in the y direction, our dispersion constant in the z direction, times e to the -1/2 times y squared over our y dispersion constant squared, times the quantity e to the -1/2 times quantity z minus h squared, divided by our dispersion constant in the z direction squared, plus e to the -1/2 times z plus h squared, divided by dispersion constant in the z direction squared, and end of quantity. That is our big, huge equation, and now we need to figure out what terms we need to find in order to go ahead and calculate this. So first of all, we have our u already. We've calculated that up here. Our dispersion constants we need to find. So if we look at our equation for our y direction dispersion constant, it's a times x to the b. And for our z, we have c times x to the d plus f. Now, if we look at the given tables again, we should have table 20.2, and so notice that we are at x equals 0.8 kilometers, so we fall in this section right here, meaning we would choose from these C, D, and F values. Our stability is D, so here we can say that A is equal to 68, B is equal to 0.894, C is equal to, so let's make sure we're following the right ones, is equal to 33.2, D equal to 0.725, and then F is equal to -1.7. All right, so we've got those values. We can go ahead and plug in here. And then the key here is that our x value has to be in kilometers when we put it into this equation. So we put in 68 times 0.8 to the 0.894, and for our y dispersion constant, we get 55.7 meters. We can do this down here, and so we put in 33.2 times 0.8 to the 0.725 power plus a -1.7, and so that makes this our z dispersion constant equal to 26.54 meters. Okay, so we've got those. We can go ahead, plug in here because we have everything else. So our y is going to be in meters, our z is going to be in meters, but our x that we use in these equations down here has to be in kilometers. So that's one kind of tricky area to make sure you understand. So we're going to put in all of our information here. So 1.5 times 10 to the 8th micrograms per second divided by 2 pi times our 4.37 meters per second times 55.7 meters times 26.54 meters. All of this times e to the negative 1/2 times 200 squared divided by 55.7 squared. All of this times the quantity e to the negative 1/2 times 15 minus 187. And I guess we should pause here for a quick comment. So the h here, we didn't quite spell out, but h here is going to be equal to h plus our delta h, which is equal to our, first of all, our h being our 80 meters plus 107 meters, and so here our h is equal to 187 meters. And so that's where we get this 187 to plug in for the h values here. So make sure you're not confusing your little h, your delta h, and your big H there. All right, so we'll square this, divide by our dispersion constant squared, plus e to the negative, move this over, 1/2, 15 plus 187 squared, all of that over 26.54 squared, and we'll close up that quantity right there. All right, so doing the math on that, we should get 4.44 times 10 to the negative 9th micrograms per cubic meter. So that will be our steady state at this XYZ point somewhere down the line, 0.8 kilometers downwind from the stack, 15 meters above ground, and then 200 meters off to the side. All right, moving on. We are almost done with this one, so we need to calculate next our maximum downwind ground level concentration. So if we look, we have a couple